All right, so what we're going to do is we're going to start every single hour of lecture by talking about three-phase. And eventually, I will get it correct. Let's see. Here we have an actual three-phase waveform that I stole from the internet rather than drawing it myself. Good thing number one. All right, and looking at this, we can now see that this starts here, and the very next one starts at exactly
120.
How many degrees apart are they? 120 degrees apart. So the notes were correct. I just can't draw because I was drawing like a, as like a, yeah, I was like, yeah, I was drawing half of a six phase. So I squeezed them together too much. So here we go. So now I've got the actual one. So I was correct. So 120 degrees apart. Not that that will probably ever make any difference whatsoever, but would not want to put out bad information. So
Diagram is not to scale.
mine wasn't. That was my problem. I even actually have in my notes one that I came off the internet, and I measured it out doing that, and it came up with that. So I must have picked up some other weird thing because it is definitely.
Power.
Yeah, maybe. I don't know. So, all right, back to. Let me see. Did we start this? Yes, we did. So we want to go to that thing. Okay, we're talking about magnetic fields. All right, good. I like talking about magnets. So magnetic field in a wire. So we had to have three things, which was relative motion, a conductor, and a magnetic field. Magnetic field, relative motion with the conductor. And we talked about the fact that in a DC circuit, when we have any sort of coil next to another coil in DC circuit, if I power this one with a battery, that we'll get a magnetic field will grow. That magnetic field grows, cuts across this, induces a voltage in this one, but only once for a split second. Because that's how long it took for this to grow. And it cut across this one. Cut across is your key word. Cut across, induced a voltage in this, then it died. And so now this one's energized, this one's dead. Then I turn off the battery, this collapses. Once again, that magnetic field, which has grown out here, cuts across these, inducing a voltage for a split second. Okay. So let me see. Magnetic field in a circuit with no voltage. Yeah, I'm not going to draw this. In a circuit with no voltage, free electrons randomly move around. Each electron has a magnetic field, but the randomness cancels each other out. So, all right. So in a wire, we have free electrons. They're just kind of bouncing around in here, just kind of, lazily moving about. And they have a magnetic polarity, and because they're just kind of bouncing around randomly, their polarity each cancels each other out, so we have no magnetic field. But once we put power into it, then all the electrons are moving, and they're in formation, doing a little, march thing. And so now they have polarity, so that creates a magnetic field because they're all doing the same thing. So now they all have their north going one way and the south going the other, and so the wire has a magnetic field. And of course, like I just said, that magnetic field, does extend outside of the wire. See, as voltage is increased, what do you think will happen with the magnetic field?
It will get bigger.
It will get bigger. The force of the magnetic field is the left-hand rule, which will not make you memorize. Wrap the left hand around a conductor with the thumb pointing in the direction of current flow, which would be electron flow. Fingers show the direction of the magnetic field. So the magnetic field is moving around this way. It's not important. Just to know that the magnetic field is there is important. So, all right, magnetic field in the wire. Do I have to write all of that? I hope not, because, okay. I saw one person say no, and I'm looking away real quick. All right.
Yeah, like a left-handed
All right.
person wrote all these rules. Yeah.
Let's talk about induced EMF. All right, so what does EMF stand for?
Electromagnetic force.
Electromagnetic force. See, as we talked about with a generator, a wire moving through a magnetic field will produce current. So it does not matter if the magnetic field is moving across the wire or the wire is moving in the magnetic field. It doesn't know the difference. It's just relative movement between the wire and the magnetic field. That produces a voltage. All right, so wire with magnet will produce voltage, EMF. With DC voltage, the voltage goes from basically 0 to maximum instantaneously, right? It's just on. It doesn't really take much time, so it's on. As long as current flows, we have EMF, or as long as we have EMF, we have current. When the voltage, this is what I just talked about a bit ago, when the voltage reaches its max and stays there, then we're pretty much going to lose the relative movement. But with AC, the voltage is constantly changing. So we go back to our loop of wire now, and we have another one next to it, which I just won't do. And now we have a wire with AC, right? And so this wire, this side's always going to be our hook to our generator now, our AC generator. So what's it doing? If I plug it in right here, I'll just do it just for demonstration.
Start a fire.
Yes, it'll start a fire. That's fire extinguisher. All right, so plug it in the wall, and what's it doing? 60 times per second.
On, off, on, off, on, off.
On, backwards, on, backwards. So yeah, it's doing this, right? So it's constantly moving. Well, so it's not like it's growing this way, then growing that way. It's going this way positive, then this way negative, then this way positive, and this way negative, and this way, right? 60 times per second, it's moving across it. It's just flipping polarity like a battery would. So it'd be the same thing if I took the battery and did 60 times per second, this way, then that way, then this way, then that way, then this way, and that way, right? Okay, so we have it doing that. So what's going to happen is it's what's in our secondary coil, if you will, because that's what it would be. The primary has the power, secondary is not the power. We're going to have that magnetic field going across this constantly, and we'll have constant voltage out of this side because of the relative movement between everything.
Every time it grows, it charges it. Every time it discharges, or it goes down. It's just like
it's going to follow it.
Is what it wants.
It's going to be doing the same thing on the other side.
So it's 1-to-1.
Oh, we'll talk about that next week. It's not. This would be, there's a ratio of how many turns on the primary versus turns on the secondary. That's next week's talk.
That's transformer,
Yes.
basically?
All right, let's see. With AC, the voltage is constantly changing, which builds and collapses a magnetic field around the wire. This creates an EMF that counters the flow of electrons. So there's an important point. So with AC, the voltage, and consequently the current as well, the voltage is constantly changing directions.
Did you say that EMF is electromagnetic force or
Yes,
field, or does
force.
it not matter?
It's force. Field is not the right word. I don't think it'd make much difference. Changing which builds and collapses a magnetic field around the wire. Okay, important point. This creates something or another, an EMF, an electromotive force that counters the flow of electrons. Which is to say, as current flows in, we have a magnetic force that builds up. That magnetic force can do one of two things. It'll either help the electrons move, which would have been really nice, or it can oppose the electrons, because think about the electrons have a magnetic force of their own, and so if the magnetic force that they created helped push them, then the world would be different. I don't know how. I suppose it would have unlimited energy, but it doesn't. It works the opposite way. The magnetic force that the electrons moving creates is in opposition to the electrons coming in. That is like a resistance.
It's like we're creating a large resistance at the same time as charging it up. Sounds kind of what it sounds like. Maybe I'm like not quite understanding.
I'm
Like
not
you're
saying-
saying the electromagnetic force
That they create.
is like then it's like super highly resistant.
I wouldn't say super highly resistant. It just opposes them. So you have a magnetic field that now opposes the incoming electrons. So they're doing their own damage, if you will. I never said it that way before, but
I don't understand. Like
So
so,
the wire that is coiled up produces a field.
yeah.
That field then stops more electrons from flowing into that same wire.
Right.
Correct?
So then does that mean that the curve kind of just tapers off because it's like the less? So you're putting in electrons flow into it, create a magnetic field, and then continue to flow into it until the field gets so strong that you almost can't pack it in there tighter. Is that kinda, I'm trying to think about it. In a
Okay,
way.
let's think of a way to think about that. So it really doesn't, in a straight wire, I believe it's negligible, not something. But if we take a whole bunch of coil of wire and you were to measure this with an ohm meter, it's a long piece of wire. You get a little bit of resistance simply because of the pure length of it, right? And so you'd write down that resistance. Like a motor has windings in it. And so your little motor that you had with your DC electrical project, you measure it, it's like, it's almost open. I mean, it's no resistance, right? Not open, but had almost no resistance. But yet, for most of you, I said, let's put the ammeter on this thing and see how many amps you draw. And so when you did that, the first thing you saw when you turned on your circuit is the ammeter went all the way over and started coming back. Well, what was that about? That was this in action. You turned on the motor, and the motor wasn't turning, and so the electrons started to flow very rapidly into these windings. Well, number one, as soon as it hits the windings, it created its own opposition within the windings that created resistance, if you will. But more so to the effect, the motor starts turning, which has another winding in it that opposed that current. So it's all you're seeing is coils creating resistance to the flow of current. So it's an electrical resistance, if you will.
So the electricity creates electricity that opposes the electricity.
Say it loud, because that was great. Electricity creates electricity that opposes the electricity that it created. Yes.
Electricity says
So it's like you're walking through a crowd. If you run really hard into it, you're gonna bump into everyone, and as opposed to slowly going through, it might not have. You might.
I have no idea how that analogy applies, but if it worked for you, that's
It's like
fantastic.
surface tension almost.
Yes.
I think what it is, the way I'm picturing it is like when you're driving and you're in traffic, right?
This sounds a lot like what he just said, but okay. But he's just going to use a car to...
Yeah, all right.
Bumper cars.
So you're driving down the street, it's a green light, but there's traffic on the other side, like past that light. So the cars are filling into that green light, but you're at the light and it's green, so you can't keep going forward because the car in front of you, like the cars in front of you are stopped.
This is funny.
I'll be in my office.
We're teaching ourselves. Yeah.
I can see their thought process. You know what? If that analogy works, they're not wrong then. All right. So that brings me to this thing called Lenz's law.
What?
Named after Dr. Albert Law, all right, which states that a change in current produces an EMF, whose direction is such that it opposes the change in current. All right, so to restate that, we have a coil of wire. So, I'm just distracted by the fact that that was a capital A and now it's not, and I didn't change it, so now I just have to wait. Things will work out by themselves. A change in current produces an EMF whose direction is such that it opposes a change in current. So what do we have with AC? Constantly changing voltage, constantly changing current. So the current goes this way, it goes that way, it goes this way, it goes that way. So Len's basically saying that this change in current, and that is change being a build up, a build down, going the other way, coming back up. Every little bit of change that it creates is a field change that happens that creates a magnetic field that makes it so that the change shouldn't happen. It's resistance to the change. Do you follow? It's kind of like if you're in a car, right? I'm just kidding.
Going 80 miles an hour and then you try hitting reverse.
So a faster cyclic rate would create greater opposition?
It does, and we're going to get into that. Yes.
Can we measure
Faster, he said, a faster change in current creates more of an opposition. Yes, it does.
So is there a graph that we can see what the electromagnetic, the EMF is?
We're going to get into some mathematical things that will help us do that.
Okay, because I was wondering if you could compare it to like an AC graph or something like that.
Well, this is AC we're using. It's just when we've added a coil, we're kind of getting to where I'm going with that. So let's see. I don't think I need to write this. If the EMF added current, it would cause runaway current, which would be really nice. When current is increasing, the EMF opposes the increased current. So as the current is trying to build, what is the EMF trying to make it do? Not build. Okay. When current is decreasing, the EMF tries to keep it from decreasing. And that happens with our coils and stuff like that too. When we shut them off, they don't want to be shut off. So as the field is collapsing, it kind of makes it so it doesn't collapse very well. So things take a little bit of time. So the EMF, or counter EMF, which is this I'm going to write. So the EMF, the EMF, or we should call it counter EMF. Counter EMF, which is also called CEMF, counter EMF, is 180 degrees out of phase with applied voltage. And I don't think that particular statement is like so important that it's 180 degrees, but it's to say that in an inductive circuit, which is coils, the counter EMF. Yeah, I'm just gonna let it go. I don't want to make a mess of that. Yes.
Would that counter EMF technically be that helping along?
Well, it doesn't help. It's the opposition. Remember, we don't get help. We get a hindrance.
This is out of phase.
I think that
Yes.
so it will always be 180 degrees to the voltage, regardless of if it's in phase or out of phase.
That makes it out of phase.
So this is what pushes it out of phase.
Yes.
Okay.
Yes. Okay.
That's why they need capacitors.
Capacitors do the opposite. We're going to go through inductors and capacitors. So the amount of self-induced EMF dependent. Okay, so the amount of self-induced EMF, that's the EMF produced in the coil, is dependent on three things. Dependent, oops, I should say, and proportional. Which is to say, we have a problem. The problem is with coils of wire in an AC circuit, the counter EMF that's produced opposes the current. That is why we have Eli. Voltage comes first, then it causes the current to lag. How bad that gets is dependent upon three things within an inductive circuit. On three things. Those three things are frequency, which is to say more changes equal more make sure I get this right, more EMF. So the higher the frequency, the worse the problem. We can go extremes. DC doesn't have the problem, right? There's my extreme on one end. The other end is kilohertz. We get up in the kilohertz range, it's going to make more and more of a problem. More changes, we have more EMF. Current flow. Oh, yeah. Current flow. More current flow equals more EMF. So the more current we have, the stronger the magnetic field, the more of a problem we have.
Would that be CEMF?
CEMF? Sure, we can call it that.
Okay.
And physical shape of the conductor.
Would it be the conductor or the inductor?
I'm going to say conductor, and I'll tell you why. Because I'm going to look at all conductors. So in a straight conductor, then counter EMF is determined by lines of flux. Wow, that was pretty good. I figured that one out. It's like this thing is learning me. Determined by the lines of flux. And there's really not many lines. So there's not much in the way of lines of flux. It's straight. So it's really not an issue. Maybe I should have just wrote that. In a straight conductor, counter EMF is really not that much of a deal. Okay? So you don't get a whole lot. But if the conductor is coiled, now we have a what?
Problem.
A coil. So if the conductor is coiled, we call that a coil. All right, so the EMF produced cuts through, there's that word, cuts through other wires at multiple points. Yes, other wires. multiple points.
So it's like amplified.
Amplified. This significantly increases counter EMF. Significantly increases CEMF. So straight wired CEMF is negligible. I wrote this, so I'm not going to write it. And coiled wires are not negligible. Which brings us to the inductor. And what is an inductor?
A coil?
Coil of wire. Just a fancy word for coil of wire. Why don't we call it a coil of wire? Well, then other people would know what we're talking about. We wouldn't make much money.
Use that jargon.
If you need a coil of wire, it has to be an inductor.
That's right. Okay. So inductance is the word. Inductance is defined as that property of an electrical circuit that tends to oppose any change of current through the circuit. All right, how much counter EMF, or we could call it inductance, so now we're kind of introducing a new thing here. We're saying, okay, instead of calling it counter EMF, we're going to call it inductance. And inductance, or counter EMF, is the same thing as really saying the resistance of the inductor, of the coil. So it is resistance. We don't call it resistance, but you can think of it as resistance. And that would be a good thing to think of it as resistance, but it's not resistance. And why is it not resistance?
It's not a
Because it's
physical
not
property.
actually resistance.
It's not actual there. Can you measure it with an ohm meter?
No.
Nope, so it's not real resistance.
So what
And
is what is the unit for inductance?
we'll get to that. So I don't know right now. I have to wait till I get that part of my notes. What is the unit for inductance? We're going to get to that. Okay, so how inductance, how much CMF inductance produced? Produced is determined by these things. One, core material. So inductors sometimes have core, or they always have a core. And these cores can be many different things. They can be magnetic, non-magnetic. We can have air. We can have an insulator. We could have, what do I have here? Non-magnetic, air, insulator. All these things would decrease. So let me see. Magnetic cores. That would be soft iron, is like the biggest one there. Something magnetic increases inductance. Makes it worse. Non-magnetic non-magnetic cores such as air or ceramic. What else do I have? Air, insulator, ceramic, or just some insulator. Decreases. And the reason why that is when we take a coil of wire, the coil, and we're creating a magnetic field, air is an insulator to a magnetic field. It doesn't like it. It wants to travel through something just like electrons do. And so if we get soft iron, which has high permeability, we'll talk about that later, and allows magnetic lines of flux to travel with ease through it, it does. And so those magnetic lines of flux can travel through that magnetic core and create their own circular pattern around it. Actually, if you've got the wire running this way, it would come out and go this way and this way around it, which amplifies the magnetic field going around the inductor, which causes it all to increase. So, so we have core material, plays a big part in this. So we have core material, core size. Yep, core 5124. S-I-Z-E. There. I tried. Core size. Number of turns. What does that mean? Turns.
How many times the wire wraps?
Yep, every time it goes around once, that's a turn. Every time I wrapped wire around this, that's a turn. And size of wire.
So number of turns would be different to the amount of loops.
No, it's the same thing.
Same thing.
Yes. Loops, turns, same thing. Yes.
So would that number of turns, would that be like number of revolutions, like one full revolution around is like one turn?
Yes.
Okay.
And I crossed this part out. You can thank me later. Determined by the formula L equals 0.4 pi n squared UA divided by L, where it takes up an entire page to explain that. So,
That sounds like fun. We're still here.
yeah, it's not relevant.
Oh, never would have done us like that.
Then I asked myself, why did I write that? I don't know. Okay. Inductance. Inductance is measured in henries.
Henry. That's a funny word. What was that name?
Henries. Named after Joseph Henry, partner to Michael Faraday, who gets the honor of capacitance, the farad. Henry is defined as a conductor has an inductance of one. Well, I'll write this. So measured in. I'm not going to write all that. So let me see. A conductor has an inductance of 1. Is it going to do it? 1 Henry. If a current change hang on. If a current that changes at the rate of 1 amp per second produces 1 volt. That is not something that I'm going to commit to memory. Oops, I'm not even done. Oh yeah, I was right. Produces, actually it's 1, produces a CEMF of 1 volt. There we go. And I crossed out this part. How can you calculate a Henry? And that goes on for a whole nother page, which we don't need to know. Because Henries are always given to you. When a coil is made, this is how many Henries that coil has.
It's a fixed rate.
It's
never
a
changes.
fixed, well, yeah, it's a fixed thing.
Okay.
Right? So, boom, it's given to you. There is a formula. If you really want to know it, I'll give it to you. Like CMF equals negative L divided by delta I divided by delta T. So we can go on and we can figure all that out. And now we don't need to, and hoorah, we can just move on. So Henry's, there you go. Now you know what it is, but you don't have to really worry about it. So, because Henry's are given to us. What else is given to us most of the time?
Shreds.
Yeah, farads. We haven't even gotten to farads yet. That's a whole other thing. So, let me see. This is a little bit of a repeat here. I don't think we need it. Inductance in a DC circuit. And I think I went over this pretty well. Oh, you're going to hate me in a second. But all right, inductance in DC circuits. In a DC circuit, the only changes in current is when what?
It's off.
Or?
On.
On. So off and on. That's the only time we get the change in current. Off and on in a DC circuit. So in a DC circuit, I already read all this, did all this. DC circuit with only resistance, this happens instantaneously. In a DC circuit with inductance, current no longer changes instantly.
Right,
So
say that again?
in a DC circuit with only resistance, when we click it on, we click it off. If we looked at it on a oscilloscope, it goes from 0 to max voltage with a DC in a resistive circuit almost instantly. At a coil of wire, it does not happen instantly anymore. It takes a while to build up. How come?
Because it's opposing the voltage.
Because we have an opposition. We have a coil now. We have, in a DC circuit, we flipped it on. Current starts to flow, creates a magnetic field that opposes the current, so it takes a while to build up. Because at some point, it stops growing, and it doesn't shrink. So it stabilizes. So we get that stabilization in there. So let's see. In a DC circuit with inductance, current no longer changes instantly. When the switch is closed, current begins to flow, but is opposed by the counter EMF at the coil, so it takes time for the current to reach max flow. It takes time. The greater the inductance, the longer it takes. When the switch is now turned off, the opposite happens. It takes time because the field starts to collapse. That collapsing field opposes the change of the current trying to die off. So it takes a while for it to die off.
That
Is that
build
co-
up too.
Sorry. What'd you say?
It's just the build up too of the.
Build up takes a while, and the fall down takes a
So
while.
it's kind of like that. If you had plugged the coil into that, it would just sort of your little
This?
You can see that.
It is, but this is a capacitor.
Yeah, exactly. So
It's the same thing.
With the so you would have, if you turned the battery on with a coil on there, that light would take time to build up, and
Build
then when
up.
you turn it off, it would take time for it to die.
Right, so it'd be this, but a little bit the opposite. It would take time for it to come to full brightness, and then it'd be full bright. It would just stay at full bright. Then when I turned it off, it would slowly dim out. And that takes some time. So the amount of time it takes, so I got to do something here. Let's see. Because this is kind of, let me see, inductance, and we're just going to call it time constants. So it takes time for that to happen. Even though I didn't write all of this, it takes time. So the amount of time it takes for current to reach, the amount of time it takes for current to increase, let me see, time it takes for current to reach maximum, or completely turn off, because we got to add that in there too. completely turn off, is based on time constants. And this is just a mathematical formula that they came up with, whoever they are, about how long it takes for this to happen on the way up and how long it takes to happen on the way down. And it takes 5 time constants. So the amount of time is based on time constants.
5 times.
It takes 5 time constants.
How long's the time?
New
Oops.
York minute.
42.
42.
For this to happen. Now, it's not, I can't give you a time because it's going to be based on a bunch of factors. We'll get into the factors, but where they come up with time, it's 5 time constants. So you figure out the constant and then it's 5 of them, and that's how long it takes. So, all right, why 5? Because now I'm going way off notes. Why 5? What's that?
Because 1 wasn't good enough.
Why 5?
Because Dr. Constant sucks.
Because
5.
because
Yeah, because-
Find out on the next episode.
it is. Let me see. I'll do this.
Wi-Fi. Next question.
Yeah. 1 time constant is 63.2%.
It all makes so much sense now.
And I'm trying to do this differently because a lot of people struggle with this, but it's really very, very simple. How long does it take for current to build up to a maximum?
5 time constants.
There's your answer, 5 time constants. How long does it take to go back down?
5 time constants.
There's your answer. All right. You may now tune me out. Why 5 time constants?
How many moments are in a time constant?
And
Let's not do this.
Why 5 time constants? Because I said so. At 63.2% of the previous value. So 1, I'm going to say TC, time constant, so I can save time in SeaWorld. 1 time constant is the time it takes for current to increase or decrease to 63.2% of the previous value. VALUE, value.
so it's a fact, pretty much a factor of or not a factor.
I'm going to show you that. Yes. So it takes 5 time constants to equal full value, which is defined as greater than 99%. So that's greater than 99% on, or full value, or 0 value, which is defined as less than 1%. So as soon as we hit anything over 99%, it's considered full on. Anything below 1% is considered full off. So if we started with full on at 100%, full on's 100%, and it takes it. So remember that a time constant is the time it takes to the current to increase or decrease 63.2%. So 100% minus 63.2% equals 36.8.
Yeah. Totally.
36.8 minus 63.2% equals It's a percent, so it worked
30.
fine the first time, but now you have to figure out what is 63.2% of that and subtract it. Follow?
36.8
And I can just tell you what that is. It should equal 13.54. Okay, 13.5. Oh, this is time constant 1, time constant 2, time constant 3. 13.54 minus 63.2% equals, I'll do the math for you, 4.98. Time constant 4, 4.98 minus 63.2% equals 1.83. Is that off?
Still off.
Okay, time constant number 5, 1.83 minus 63.2% is going to equal 0.67. Is it off?
Now it's off.
Less than 1%. And it works the same way building it back up.
So you have like a 2. You really have a 2% margin of error. For
Sure.
lack of a better term.
Yep. So how many time constants does it take?
5.
That's all you need to know. Now you know how it got there, but you don't know why they decided it was 5. You don't know why they decided it was 63.2. It just showed you how the 63.2% works. But why did they figure out 5? I don't honestly know that at this point in my life, and it does not matter. But there you know, it takes time. The point is, it takes time. So why do we go through that exercise? Because it takes time for current to build up. If it takes time for current to build up, the voltage will be in front of the amps, which will cause them to be out of phase. So why 5? Because 1 times 6. Okay, so I'm just going to leave that at that. And I'm going to come over here, and we're going to talk about something that is actually important. So a time constant is proportional to inductance, which means that the more inductance we have, the longer it's going to take. Longer of those 5. So it takes 5, just takes longer 5s. Proportional to inductance, and inversely proportional to resistance. Which is to say, more inductance, and inductance is measured in what? Henries. Equals longer time more resistance equals shorter time. And I probably don't need to get into this. The formula is, because it is like time to go, so there we go.
That was time constant about
Wait, just one time constant.